The 2017 AP1 Problem 4 inspired me to make a simulation. It's a classic question I like to call high road versus low road. You have two blocks. They start at the same height, they end at the same height, but how they get there is very different. They're going to land the same distance apart because they have the same speed, the same change in energy, similar to a roller coaster. Here's a video I made a couple years ago, or 6 years ago. Up until this point, they should be tied. The high road's actually a little ahead. Theoretically, they should be the same. And then what happens next is the low road overtakes it. The reason being, everywhere that the lower track is lower, it has less potential, which means it has more kinetic, which means it's going faster. Yes, it does slow down as it goes uphill, but it slows down to the same velocity that the top ball already had. Energy gives us the answer of who wins, but it doesn't necessarily tell us exactly how much time it's going to take to get to the end. So I made this simulation, and in this simulation, you've got an image of both tracks, and then you can move these little dots to model the layout of the track. In a little bit, I'll explain how the simulation works, but you can see that the orange track took about twice as long as the blue track. The 15 meters high is kind of arbitrary, but I mapped it right on top of the picture, so that works out pretty well. So then I thought, well, what if I was to take a picture of that same marble race from 6 years ago and try to simulate it with this simulation? So the orange is the low road, the blue is the high road. The results you get are 1.78 and 1.58 seconds. So it definitely has the low road winning. To test this in real life, I did 10 trials for the low road and 10 trials for the high road with this photo gate, and these are the times I got. The times I got, it was pretty consistent. The average standard deviation, and now the simulation, I'll get to this a little later, but when you include the fact that it's rotating and has rotational inertia, we got 1.58 versus 1.687, and 1.78 versus 1.824. So not bad. Theoretically, I was getting that they should be about 0.2 seconds apart, and we were actually getting a little closer to 0.14 seconds, but that's still pretty good. I was impressed with the simulation. But I suppose it's not that hard to be impressed with yourself. Again, so here are the results from the simulation. You can see that the lower track, the orange track, did go a teeny tiny bit farther, but it also went faster. Now, if you look at a graph of, now this isn't speed versus time, this is speed versus position. In the beginning, when they're sloped the same, you can see that they pick up speed, and they're at basically the same speed until this is the location at which you start to go down that dip. So here where you're starting to go downhill, you're also starting to pick up speed, and here where you go back to the same height, you start to reach the same speed. So this confirms what we already discussed. In terms of acceleration, you can see the blue, it's accelerating, and then it's basically not accelerating. It's going at constant speed because it's flat. The orange and the blue are both accelerating, but then you get this dip for the orange where it goes downhill, and you get a positive acceleration. It speeds up. But then here you're going to get a negative acceleration, and it slows down. And then again at the end here, the little blip here, you don't get any acceleration. So this is consistent with what we saw when we did it for real. So if you're still wondering, you may be wondering, how did we do that? I get the velocity due to the energy, but how do you get any information about the time and how long it took? So what we did remember was we broke it into 20 line segments. So let me just show you just the orange track for a second. By dragging these dots, you're getting the exact positions, x and y coordinates of the ramp itself. Now, what I do is I assume that in those in-between spaces that it's a constant acceleration. So we basically assume the path is like this. Now, at this point, it's going to be constant acceleration. So what I do is I get the velocity at the initial part of that interval and the velocity at the final, and we do that from basically just energy conservation. mg times the change in height, and assume all of that energy is going into kinetic energy. So basically the kinetic energy at point 2 plus the change in mg times the change in height, which is going to be y3 minus y2. Assume that is going into the velocity at point 3. Then what I say is the average velocity for segment 2, meaning going between point 2 and point 3, is going to be the velocity at 2 plus the velocity of 3 over 2. You may recall that for constant acceleration, the displacement is equal to the average velocity times the time. So the displacement in this segment 2, meaning going from 2 to 3, is the same as the average velocity for segment 2 times t. So the time to complete segment 2 is the distance of 2, meaning segment 2, over the average velocity of segment 2. Because we're treating this segment as a line, I can say, well, this distance d2 is basically just the hypotenuse of a triangle. Pythagorean theorem, change in x squared plus change in y squared, square root is the distance there. So to get the total time for the trip of the marble, the cumulative time is equal to the sum of all of those line segments from the first segment to the last segment. Now I'd be saying that's fine, but what if you had friction on the track? How does that change things? I thought about this and was initially wondering, well, the angle's changing, so the friction force is changing, and I thought it might be really complicated, but then I thought it's actually kind of simple if you think about it like this. Imagine it's like an incline where you've got the weight force, normal force, and friction force. If this angle is theta, you'd say n equals mg cosine of theta, and f equals mu mg cosine of theta, because it's mu n. But this theta, the cosine of theta, this distance delta x, and the length of this side is d. So that means that the friction force is actually equal to mu mg, and instead of cosine theta, I can write delta x over d. Well, the work done non-conservative by the friction force is going to be equal to negative mu mg cosine of theta, which is delta x over d, times the d to get the distance. Remember, work is force times distance. These cancel out, so I believe the non-conservative work only depends on mu mg and the horizontal distance that you travel. It doesn't actually matter how much the angle is, only the change in horizontal position, which is kind of neat. I'd never thought about that before. We'll get to the friction in a second. All of these x's and y's you can change by moving the dots around, or you can manually type them in the x and y positions, but it's easier to move the dots. This is like we were talking about with the distances and the energy. Now, I will say that friction term that we were talking about here, so instead of taking the change in energy from the very beginning, you take the change in energy from the previous point, and then you subtract any work done by friction here, which is just going to be mu mg change in x like we talked about. If I'd stopped there, you can see my times here would not have really matched there. They're sort of kind of close, but not satisfyingly. Now, what's different here than in the problem from the AP is this is actually a ball that's rolling on an incline, essentially. And when it does that, we're going to assume no slipping. So in the special case where there's no slipping, the translational velocity is equal to the angular velocity times the radius. So we only care about, as far as when it finishes, the translational kinetic energy. Any kinetic energy that goes into rotation isn't going to speed up the progress. So if we take a ratio of the translational 1/2 mv squared to the total, which is the 1/2 mv squared plus 1/2 iw squared, and you put in w as v over r. Now the I like to express as a fraction of mr squared. So like for a cylinder, that's 1/2. For a ring, that's 1. For a sphere, which this is, it's 2/5. And that simplifies to this. So this is the fraction of the kinetic energy that actually gets to go into translational velocity. So in our simulation over here, instead of just going kinetic, we're going to only get a fraction of that goes into the translational velocity. So this is what we use for the velocities. And when we do that, it cleans up our results quite a bit. So with that, this is much closer than when you don't include the rotational inertia. In fact, we're getting the measured result for the distance was about 6.8 and about 2.4% longer than what the simulation said it should be. And honestly, with my ability to measure the horizontal distance and the heights and doing it by the photograph, I would think that's well within my uncertainty. So I'm definitely happy with how this turned out. So again, just to show you, if you lower these dots, number them as if it's a bigger dip, you can see that's decreasing the time just like we would expect it to do. You can also add in the simulation your own photograph to lay this on top of. So you got these images, like this is the image you can turn on or off. These are parameters. F is the moment of inertia coefficient. Mu is the friction. You know, like let's make the moment of inertia fraction 0, but then watch what happens when you add some friction. So if we look up here, it's saying 1.32, and then if I go down here and I change the mu, give it, you know, some significant mu, what that does is it makes it, sorry, I moved some dots around. So if it's 0.89 seconds now, and then I make the friction even a little greater, and then I go up here, and it's going to change the time. Well, I'll have to play with that later. But nobody's probably listening at this point anyway. But I had fun with this. I thought it was a good simulation. Hope somebody out there finds it as